Okay. So it's extreme black today, and I am in extreme black. As my calculator kind of didn't go in extreme black, but it's pretty close. All right. So rational functions. So rational functions are of the form where I have a polynomial divided by another polynomial. So if we remember what polynomials are, they might be something like x squared plus 3x plus 7 divided by, I have to have another polynomial, not just a number. So I could divide by x, and that would be a rational function. So I'm going to say this is a polynomial divided by a polynomial. And we're usually going to go for, when we're dividing by the polynomial, I'm going to call it a rational function if the polynomial in the denominator has a degree 1 or better. It's really going to be a rational function. Otherwise, it's way too simple. Yes? These are called rational functions. When do we use rational functions? They describe a lot of different kinds of mathematical models, different kinds of physics and stuff. They're not straight. They're not always these straight line functions. These are the functions that will give us our interesting curves, like this one here, that we might need to describe something in real life that doesn't just follow a straight line. Okay, or the funny curvy lines that just a plain old polynomial would give me. These describe things a little bit more complicated, so we're getting to a little more complicated functions. Okay, so here's a rational function, negative 2x over x squared plus 1, and I don't care if my batteries are low. All right, graph. There we go. And there's its graph. And this is not a graph that I would ever have you make by hand. And it's kind of a strange one. On the left side, as you're getting more and more negative, you are getting an asymptote on the x-axis. You're getting a horizontal asymptote, getting closer and closer. And then what I'm thinking about on the right side of this graph, on the positive x's, it dips down and then comes back up and gets an asymptote on the x-axis again on the other side. Very unusual. Haven't seen something like this before. Okay, so this one has some funny horizontal asymptote. All right, so another strange example. Let's see if I can grab this one real quick. Is this 1 over x squared minus 4? Another strange looking graph, but might really mimic what you're looking for in a mathematical model. It actually has this little funny line that's coming down the graphing calculator isn't actually there. It's the graphing calculator making a mistake, which it does from time to time. This one has a horizontal asymptote. As my x's are getting more and more negative, I'm flattening out on the x-axis. And on the horizontal asymptote on the other side on the x-axis too. And it also has 2 vertical asymptotes. And the asymptotes are happening around the numbers -2 and +2. Because if I square -2 and subtract 4, I get 0. So I have that 0 thing in the denominator like we dealt with yesterday's functions. So that makes a discontinuity in my graph. It's continuous over here on the left, and then all of a sudden it doesn't meet up anymore. It takes a big split between positive infinity and negative infinity. Starts again here at negative infinity, goes up, kind of looks parabolic. Gets another asymptote over here because 2 squared minus 4 is 0. So it's heading to negative infinity over here, and then boom, all of a sudden it pops up here at positive infinity and starts coming back down. Devin, you have an immediate. I don't know what that's about. Okay, so another strange one. This has both horizontal and vertical asymptotes. I don't know. Yeah. Okay, here's another weird one. This has y equals x plus 2 times x minus 1 over x plus 1. And you've probably never seen one that looks like this. Let's see. So I'll show you what it looks like. Okay. This one's a little weird again. It actually is going up like this. And, whoops. Get that asymptote. And up like this. And again, your calculator often makes mistakes on these whenever you have asymptotes, vertical asymptotes. Your calculator tends to make a mistake. This one has a vertical asymptote right here and no horizontal asymptotes. Yes? How do you know what? So what we do is we're going to analyze things. If you've got vertical asymptotes, and we'll find out when you have a vertical asymptote. And if you do, your calculator will usually make a mistake and show it as a solid line. So you'll identify a vertical asymptote, and then you'll look at your calculator and go, okay, that was the vertical asymptote, and they made a solid line. I should make that into a dashed line. So we'll do a little analysis before we graph them on the graphing calculator. Okay. And then last one. Let's see what I used here. I'm kind of showing you as example for what we're going to get into today. And I don't know that you need to. Come on. Last one doesn't look so unusual. It's x plus 1 over x plus 2 over x minus 1. It looks like a line, even though the equation doesn't look like a line. It really looks like a quadratic on the top and linear on the bottom. But this graph is deceptive because even though it looks like a line, it isn't, because my function, if I put negative 1 into this function, I get 0 on the bottom of this on the bottom of this fraction, 0 in the denominator. 0 in the denominator can't happen, so I can't use an x minus 1. I don't get an asymptote in this case. I get just a little hole. So I can't include this point. This graph includes this entire line except this one point at x equals negative 1. What's that? How does that? Okay. Why does this graph end up looking like a line? Because these two cancel out, and it ends up looking like x plus 1, x plus 2. Looks like the line x plus 2. Y-intercept of 2, slope of 1. But because my original function was actually a rational function that had an x plus 1 on the bottom of the fraction, I cannot let the bottom of the fraction be equal to 0. So if x is negative